Simple one. All right, problem 3. A population of insects in a region will grow at a rate that is proportional to their current population. In the absence of any outside factors, the population will triple in 2 weeks' time. Sounds terrifying. On any given day, there is a net migration into the area of 15 insects, and 16 are eaten by the local bird population. And it gets worse. 7 die of natural causes. Okay. If there are initially 100 insects in the area, will the population survive? So that's an interesting question. If not, when do they die out? We're going to try to solve this. I didn't do an Excel numeric for this. You can pause here and try to kind of do the same thing we did for the mixture problems to see if you can anticipate an answer. But you can do it. I did it on my own. I'm just not going to include it in the slides. You do get something similar to the answer. All right, so here we go. T is time in days. Let's P of T be the population of insects at time T. So let's start by looking at the birth rate. We're told that the insects will be born at a rate that's proportional to the current population. So R times P is the birth rate. And then the initial value problem is not going to be as tricky as in the other problem. So the change in the population equals, so first let's address the insects being added. Again, you don't know how many insects there are at any given time, but that's okay. That's what you're trying to find out. So R times P, insects are born, plus 15 migrate, minus 16 are eaten, and 7 die. So you get P prime equals RP minus 8. That looks simple. And then P of 0 is 100. So I can solve this. The only problem is I don't know what R is. And that's where we're going to use the second sentence where it says, in the absence of any outside factors, the population would triple in 2 weeks' time. So that means we're going to ignore the plus 15 minus 16 plus 7. We're just going to write P prime equals R times P to solve for R. Okay, and then we're going to come back to our differential equation. All right, so this in itself is a differential equation. This you know how to solve. That's how you get an introduction to E, right? So P prime divided by P equals R. It's a separable equation. Integrate each side of the equation. You get ln of P equals R plus C. You can add the C on the left or right. The convention is to add it on right. Raise each side to E. You get P equals E raised to R plus C. You get that. Then you can apply the initial condition. Or rather, it says that after 2 weeks or 14 days, there'll be 300. So you can do that. And then you can figure out what R is, right? So R is natural log of 3 divided by 14. Okay. All right. So now we're ready to solve our initial value problem. This will get more interesting, I promise. Okay. So solve the initial value problem. Here it is. P prime minus, right? I'm going to write this as ln of 3 divided by 14 times P minus 8. So P prime minus ln of 3 divided by 14, P equals negative 8. This is another linear differential equation. Here it comes again. Because we're adding and subtracting things, that's why. So these are kind of similar to the previous, to the mixture problem. All right. Actually, almost identical. It's just in this case, the birth rate is a constant. The birth rate could have as well been a function of cosine as well. Like, let's say the birth rate is seasonal, so it goes up and down. All right, but anyway. So, all right, so here's our linear differential equation. Here's our initial value. So we're going to solve this. Introduce integrating factor. Mu of t equals e raised to the integral of this. So e to the negative ln of 3 divided by 14 t. Rewrite and integrate. You can pause here to see if you get this answer, but remember, you multiply everybody by the integrating factor. You get the product rule on the left. You get negative 8 times e to the negative ln of 3 divided by 14 t dt. This is an easier thing to integrate. Okay, so you get P of t equals 112 divided by ln of 3 plus c times e raised to ln of 3 divided by 14 times t. Okay, what did they ask us? If there's initially 100 insects, will the population survive? So what do we have to do? Oh, we have to figure out what C is. Okay, so apply the initial condition. P of 0 equals 100 to get the particular solution. So, am I skipping a step? P of 0 equals 100 means C is going to equal 100 minus 112 divided by ln of 3. You can, I skipped a step. So you can kind of figure it out, right? Because if you plug in 100 here, You can subtract, right, and then divide by C. Okay. 100 here and then 0 here, so it'll be right that. Okay. Okay, so let's graph the particular solution, and this is what the graph looks like. All right, sad news for the insect population. It does look like it dies out. And if you did the common sense check, did you get around 50 days? It looks like the insects will die out in around 50 days. All right, this is where it gets interesting. Test your, I guess, intuition. What if I told you the initial population was 105 insects? Do you think they would still die out? It seems like the answer is yes, because this is a pretty dramatic decrease. And I mean, is starting higher really going to change things? Maybe they'll last for like a day longer or something. So how would you answer this question? Well, you take a look at the general solutions. All right. So okay, I'm going to, in order to study the behavior of the general solutions to that differential equation we wrote, I'm going to use an online slope field grapher. And there's a few online. I've tried a bunch of them. I like this one the most. You can see the solutions, the behavior solutions, the best on this one. So I'm giving you, this is the address. All right. So all right, here we go. So this is my general solution. We said if the population starts at 100, it will die. So my question to you was, what if the initial population was 105 insects? Would they also die? All right. So let's take a look at. So I'm going to at the direction field, right? So I'm going to put P prime equals ln of 3 divided by 14P minus 8. This is what the direction field looks like. This is kind of interesting because it kind of looks like that there's a point, right? It looks like the equilibrium solution exists somewhere around 100. And then if your initial population is below that point, then you die out. You eventually, I mean, you decrease to infinity, but we know that the x-axis represents death in this case. So you die out, or the insect population grows unbounded. Okay, and then you can that graph I talked to you about also has a way to graph particular solutions. So I did, and this kind of looks interesting. Now it kind of looks like the equilibrium solution exists at 100, but we know that's not true because at 100 it actually went down. So this might be our solution. So what I'm going to do is I'm going to zoom in a little bit closer to 100. So if you zoom a little closer on the slope field, you can see that the equilibrium solution exists at 102. So if you're starting with 100 insects, you are doomed. Your insect population is doomed to die in 50 days. If you're starting above 102, you will, your population will grow forever. So that little change in initial condition ended up being consequential. And then you can kind of test. So the equilibrium solution occurs at y equals 0 is 102. So what it means is if your population actually starts at 102, it's going to stay the same. It's going to stay the same, right? Because equilibrium solution means y prime is 0. So if you do start at 102, the solution is going to stay the same. But let's test our p of 0 equals 105. If you put that in, this is your particular solution. P of t equals 112 ln of 3. And if you graph it, this is what you get. So you actually get infinite growth. And this is never equal to 0. All right. So that's interesting. So I did say equilibrium solutions do take on... become more meaningful when you actually do an application problem. So in this case, an equilibrium solution told us what the initial population has to be for the insect population to survive under these conditions, right? And then you can mess with it a little bit, of course. You can increase maybe migration, or you can, I don't know, kill the birds that are eating them. Probably don't want to do that. Well, I guess that's all you can do, increase the migration, because you're not going to grant them immortality, and you're not going to kill the birds. Okay. But yeah, okay. All right. So it's